Another application of combination is in a very interesting situation. For example, I want to find the number of whole number solutions to, let's say, an equation a plus b plus c is equal to 7. So how many whole number solutions exist to this equation? By whole number solutions I mean a, b, c are whole numbers, and as we know whole numbers include 0 as such, but they can't be negative. The solution to this question is through an analogous way, and that analogous way is this 7 I have to sort of distribute it between the three A, B and C. Can I give a 0.5 to C? Not really. Since it needs to be whole number, I can only give in units of 1. So one way is to consider the 7 as 7 different ones. 1, 2, 3, 4, 5, 6 and a 7. Now that I have split it into 7 ones, the least unit that I can give anyone. Second task is I need to break this up into 3, and the approach to do that is called a partition method. So I am going to use a P as a partition, and I am going to partition this into 3 groups. To partition something into 3 groups, how many partitions would we need? We would only need 2 partitions. So the solution that we are talking about is 1, 2, 3, 4, 5, 6, 7, and place up 2 partitions anywhere. For example, I place a partition here, and let's say I place a partition here. P stands for the partition. Anything before the first partition is given to A, that between the 2 is given to B, and that after the second one is given to C. So this results into a solution of A gets 2, B gets 4 and C gets 1, and we ensure that the summation of it is 7. Let's take another way of partitioning. So we have a 1, 2, 3, 4, 5, 6, 7. What if I would partition it as a P out over here and let's say a P in the end? Could I have a partition in the end as well? Anything before the first partition goes to A, that between the 2 goes to B, and that after it goes to C. Is this acceptable to me? Pretty much, right? So when I meant by an analogous way, what I meant is the number of ways in which we can partition is equal to the number of solutions that we get here. For that, we need to ensure that there's a 1-to-1 correspondence out there. So for example, let me take a solution here, 5, 1, 1. Am I reasonably sure that this solution can be resulted in only one partitioning method? Pretty much, right? So what is this? 1, 2, 3, 4, 5, 6, 7. The first one needs 5. 1, 2, 3, 4, 5. So put a partition after that. The second one needs 1. So put a partition here. So if each solution refers to just one partition, each partition refers to just one solution, then the number of partitions will be equal to the number of solutions out over here. Hope you get that. 5, 1, 1. Is 1, 5, 1 different solution? I have used A, B, C. A being equal to 5 and A being equal to 1 is a different solution. And how do I get this? Say 1, 2, 3, 4, 5, 6, 7. The first one needs 1, so the partition comes here. The last one needs 1, so the partition comes here. So 5, 1, 1, 1, 5, 1 are resulting from different partitioning ways as such, right? Now to find how many ways. Well, this is pretty easy. 7 ones and 2 partitions. One way to look at it is I need to arrange this in every possible way. This is similar to like arranging Mississippi, where many of them were alike. So how many of them? 1, 2, 3, 7 and 2. That is a 9 factorial divided by 7 factorial, 2 factorial. And this is going to be my answer in this case. Right? So I prefer using it this way, 7 ones, and to make it into 3 groups, 2 partitions, 7 and 2. There is an alternate way also. In every of this, if you look, there are 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 positions. What are those 9 positions? The 7 ones and 2 partitions. So out of these 9 positions, any 2 could be partitioned. So I could also use the, this is the way formulas are given in the textbook. So I could also use 9C2, which is exactly same as the previous answer that we have got. Hope you get the idea out of it. Let's try it with one more question, exactly identical, just to make sure that we can use it very fast. So the next question, where I'm not twisting anything as such, is the number of whole number solutions to A plus, okay, let me write it below itself. The number of whole number solutions to A plus B plus C plus D is equal to 15. Just to be quick out over that, 15 ones. To make them into 4 groups, I need 3 partitions. So 15 and 3, that is 18 objects. However, 15 of them are alike. All of them are ones. And the other 3 are partitions. All of them are also alike. If I just change the partitions amongst themselves, it should not result into a new solution. So I treat them as alike. That is 3 factorial. This is the answer. The other way, 15 ones and 3 partition. That is 15 and 3 is 18. Out of them, 3 positions will be partition, which is 18C3, whichever way you look at it. So what are the twists that can come to these questions? There are plenty of them. There's a whole range. We will not be able to cover entire thing. So one of the twists is, what if I don't need a natural number solution, whole number solutions, and I need a natural number solutions to this? So now, one way to think is to exclude all where 0 comes in, but there could be plenty. 3 of them could be 0, 2 of them could be 0. Which 2 are going to be 0? So there's many ways in which you would have to subtract out with that. A simple way is, the moment we have a natural number, could I say the A is nothing but the minimum value is 1. So let it have 1 and let it have something other than 1 as well. So if I say the solution is 8, A is 8, it would be 1 plus 7. If A is 1 itself, then A prime will become 0 in that case. So by the same logic, I could write B as 1 plus B prime, C as 1 plus C prime, D as 1 plus D prime in this case, right? And the equation now turns down to be this is equal to 15. After rearranging it, I simply get A prime plus B prime plus C prime plus D prime is equal, this is not raised to 1, this is just a prime, is raised equal to 11. And what is interesting is now each of A prime, B prime, C prime and so on could be whole numbers. They could also include 0. So this is turning it back to the original question that we had. 11 ones, 3 partitions. So that is going to be 11 and 3, 14 factorial by 11 factorial of a kind, 3 factorial of a kind, or 14C, 3 by the direct formula as such if you want. This approach is not just limited to natural numbers. You could have any condition. For example, if I say A has to be greater than equal to 2, it hardly matters. You could just put A as 2 plus this, 2 plus A prime equal to 2. Okay, so it could also be equal to 2. Yes, pretty much. So A prime could be 0 as well in this particular case, right? So I would, a 2 is out over here. So this is going to become a 10 and accordingly your answer would change in this particular case, right? So any less, A being greater than, if there's any floor level for any of the variables, we can easily handle it in this case. There are some more ways, some more questions that could be formed in the straight way. Just to give you a quick idea. How about if I say, let's say all of them needs to be, okay, I'll have to change the equation. So let me just change this equation. I need whole number solutions to A plus B plus C is equal to, let's say, 16, and I say such that all A, B, C are even. So if all of them are even, You replace an A with a 2A prime. Even numbers can be represented with a 2 dash. B could be replaced by 2B prime and 2C prime. That would ensure that they are all even. And so 16, which simply boils down to an equation, A prime plus B prime plus C prime is equal to 8. And the number of whole number solutions to them is going to be 8 and 2 partitions, that is 10, C, 2. In this case, if I have a solution here just as 1, 2 and 5, the original solution to them is going to be, 1 is going to be twice, A is going to be twice of A prime, that is 2. Let me write it over it. 2 2s are 4 and 5 2s are 10. And will they add up to 16? They obviously need to add up to 16. Could I have an odd number solutions also? Let's try it. Just see. Let's see what happens. So I'm changing the question to such that A, B and C are odd. If they are odd, could I write A as 2A prime plus 1, ensuring that A prime can be 0 as well. Okay, and I could write as 2B prime plus 1 and 2C prime plus 1. And on rearranging this, there's an interesting thing that happens. I get an equation 2A, B and C dash is equal to 13. Now, but 13 is not divisible by 2. So I cannot proceed in this case. That should set your thinking. How could 3 odd numbers, could they add up to 16? If you have an odd number, the addition of 3 odd numbers have to be odd. So all 3 of them cannot be odd. This is what this equation is telling. Anyway, so there could be many of such variations out over here. What next do we learn is, there are applications of this even in worded questions. We'll just do 2 worded questions. One of them a cat question, this one. A bakery, let's say, has 4 varieties of pastries. Varieties of pastries. So there are 4 varieties of pastries, and it's also given each variety having quite many numbers, many number of pastries. So this is not a problem. I want to purchase 10 of them. I want to purchase 10 pastries such that I get to taste, let's say, each of them, each variety. And the question being asked is, in how many ways can I make the purchase? How many ways to purchase? So this is the worded question. Think about it. How will a purchase be different from another purchase? Let's say there are 4 varieties. Just for simplicity's sake, let me say A, B, C, D varieties. You could even use a chocolate and a strawberry and a pineapple if you're too hungry, let me say. So let's say A, B, C, D are the 4 varieties of pastries. I buy one of each, and then to make it 10, I buy 7 of this. This is one particular way of purchasing. How can a purchase be different from this? It can be different only if I buy different number of pastries of any of them. For example, I could buy 2 of them, 6 of them, this would become different. So what this is suggesting is, let A be the number of pastries of first type. Depending upon the number, whether it's 1, 0 or so on, I could get a different pastry, different purchase. B be the number of second and so on, and from here it should be pretty obvious that the sum of them has to be 10. And what do I do with such that I get to taste each variety? Each variety simply suggests that I need a natural number solution to them. I cannot buy 0, natural number solutions. And how do I get a natural number solutions? From the 10, give each of them 1, 1, 1. I would be left with 6, and the natural number solutions is changed to a whole number solution. Now, how many whole number solutions? 6 and 3 partitions, that is going to be 9, C, 3. Or a 9 factorial, 6 of them are ones and 3 of them are partitions in that case. So this is the answer out over here.